Good morning, everyone. Today I'm gonna talk more about the torque, and then this is gonna be the last section of the chapter 7. And this is nothing but the application about the torque that you learned the last time, right? So for example, here you have a 3.2 kilogram flagpole, extends from the wall with an angle 25 degrees from the horizontal, right? Its center of gravity is 1.6 meter from the point. So the here center of gravity is 1.6. So this is basically the center of the gravity, and then the distance r here to here is a 1.6 meter from the wall, right? So then the weight is acting right over here, right? So what is the torque on the flagpole about the point to the attachment? So the torque, as you learned last time, is the RF perpendicular, right? So the R here is the distance from the hinge to the point where you apply your force. So R is a 1.6. And then force, magnitude of force is of course the mass W, right? Weight of this flagpole, which is a 3.2 times a G, which is a 10, right? So this is straightforward. But the thing is, F perpendicular, right? Perpendicular to this pole, right? So you have to decompose your weight into two components, right? Which is a perpendicular component and this horizontal component. But basically, this horizontal component does nothing, so you have to find this vertical component. So then now you see this is theta, so this is 90 minus theta, so this is a theta again, right? So then this length is a hypotenuse W times the adjacent, so it's a cosine 25. So this is the answer, right? So now you see 1.6, 25, right? And then the sine thing here is what the whole pole is gonna rotate clockwise, right? So the direction of the torque is gonna be minus. Again, if you have a torque, if you have an object, rotating counterclockwise, that's a positive torque, right? Clockwise, negative torque. Simple example. And another example is a seesaw, right? So Emma and Noah on a seesaw, right? Noah is 22 kilogram, seated 1 plus 6 meter away from the pivot point. Emma 25 heavier. So wants to see the point where he makes a seesaw to balance, right? So then now this is the picture, right? So this is a hinge point, and then this boy 22 kilogram sitting 1.6 meter away, but the Emma 25 kilogram, which is a little bit heavier, so the distance from here to here, as you know, is gonna be shorter, right? But now you can also talk about calculate the torque, right? Because of this Noah, the whole seesaw will rotate counterclockwise. So that means Noah will apply counterclockwise positive torque, while Emma will rotate the seesaw this way, which is a clockwise, so negative torque. So the torque, these two torque must be balanced. Again, torque by Noah is what? R 1.6 times the force is his weight, right? 22 times 9.8 or 10, right? So this torque, which is a counterclockwise, so this is a positive torque. And then minus m mass torque is what? X is what we are looking for. And then 25 and 9.8 is gotta be 0. So then now you cancel. And at the end you see XE is gotta be 1.4 meter, which makes sense because why? The distance here for heavier object is a closure, right? So your experience, you know that, right? Because you're heavier, you have to sit close to the pivot point. Okay. And then the last one is about the rotational force and rotational mass. rotational acceleration. It's everything about the rotation. So basically, we have a basic equation for the circular motion, x equal r theta, right? So you have a circle, x is a arc length, and then angle is a theta, radius is r. So then they have this relationship, especially when the theta is a radian. So if you divide both sides by t, left side is a velocity, right side is a r omega. And then if you divide by t one more time, left side is a, right side is r alpha. So this one is called angular velocity. This one is called angular acceleration. That's what you learned, previously, right? So then you see, and then you know that this x corresponds to theta, v corresponds to omega, a corresponds to alpha. And then another thing that you just learned is what? This the left side is a linear motion, right side is an angular motion. So if you compare these two, linear motion you have a force, and then angular motion you have a torque, right? And then linear motion, Newton's second law is F equal ma, right? Newton's second law for the angular motion, rotational motion. So torque gotta be something times alpha. And this something corresponding to the mass of linear motion is called moment of inertia. So this is kind of a rotational mass. Okay. And this is now let's talk about Newton's second law for the rotational motion. So now you see every single object, M1, M2, M3, they are all rotating together once this rigid body rotating together. But the thing is that they have so if they are rotating, their speed, angular speed omega, it does not depend on the particle here, right? So every single particle on this rigid body, they have the same angular speed and angular acceleration, right? So that means your torque, you see, is going to be m1r1 squared times alpha. Torque 2 is m2r2 squared times alpha. So then in other words, your torque, net torque, corresponding to Newton's second law is what? Alpha, which corresponds to A. So again, your Newton's second law is the ma, right? So F corresponds to torque. And then A, instead of A, you have alpha. So what corresponds to the mass for the rotational motion is a mr squared. Okay, so that is called moment of inertia. Again, this is a rotational mass. Okay. And then of course this one is depends on the axis of the rotation. Okay, so then now you can say this is a Newton's second law for rotation. Torque is I alpha, or F is the corresponding equation for this one. Linear motion is A is F net over M. So for example, so what the physical meaning of momentum inertia here. So let's assume you have three persons sitting on the merry-go-round. And then the only thing here you change is their location. And then which one is easier to rotate? So as you see, based on your experience, you know this is harder to rotate, right? This is easier to rotate it. So which means even though their total mass, case A and case B, their total mass we didn't change, right? So total mass are the same, but the difference is here is the distribution of a total mass, right? So basically, this is your pivot. So that means if you have a mass distribution farther from the center of the axis, this is a rotationally heavy, right? So in other words, in order to have a rotationally heavier object, you have to redistribute the mass, right, farther from the center of the axis. Okay, so that's why your moment of inertia is proportional to mr squared. So if you have a more R, greater R, your I will increase as a function of R square. Okay? So this is the comparison. Force, torque, mass, moment of inertia, A alpha. So your Newton's second law is again same thing. And then we're gonna do the same thing for the rotational motion. Whatever you did, the linear motion, everything are the same. So for example, this is a momentum with inertia of common shapes. For example, in a thin road, your momentum of inertia is 1/12 ml square. Thin road, 1/3 ml square. In a slab, 112 ma square. Right? And then you have another values here, but make sure you don't need to memorize these things, in the exam in general, whatever, you do homework, this value will be given. Okay, so you don't need to memorize it, but you have to have a clear concept about this. Okay, they are always given based on, and then they are different based on the shape of your object. Okay, so this photo shows high wire worker, crossing two cliffs, right? Grand Canyon. And then now you have you can model the body, man's body, 1.8 meter long, 88 kilogram, and it comes with a uniform load, right? And then the pole is 9.1 meter long, and then the mass of the pole is 20 kilogram, right? So what is the moment of inertia of his body and of his pole? So moment of inertia, his body, we can treat this body as a uniform load. So then you see uniform load right here. Like this, right? So the uniform load here, the man's body about the end of the axis, right? So the moment of inertia is a 1/3 ml square, where m is his mass, L is his height, right? And then the pole is a pivot about the center, so moment of inertia is a 12 ml square, 1/12, right? So this is like this one, right? 1/12 ml square, right? So then we can simply calculate it, right? So their moment of inertia of the man is gotta be 1/3 ml square, 1/3 m. L is his height. So you have a 95 kilogram meter square. This is the moment of inertia of the man. And the moment of inertia of the pole, you see 1/12 ml square, which is a 140. So you see, even though the actual mass of the body is, roughly 4 times, even more than, basically 4.5 heavier, its moment of inertia for this pole is much greater than this. Why? Again, moment of inertia depends on the mass distribution, right? So from this human's body, we assume this is a human body, right? And then this is the axis, right? So then now you see mass distribution is very close. Most of the masses are very close to the axis. That means R square value is very small. So that's why moment of inertia for this human is smaller, even though its mass is high. But now think about this bar. The bar is relatively really long, and then this one here. This is your axis. So that means mass here is far, far away, right? Compared with this distance, just a few centimeters, right? So this is a meter scale. So the most of the mass, a lot of masses are distributed far away from the axis, right? So that's why this is heavier. Okay. Okay, so this is end of the chapter 5, and I'll assign another homework for chapter 7. Sorry, it was chapter 7. And let me know if you have any question. Okay, and then also please complete your course evaluation if you can. Thank you.